Okay, today we're going to talk about the electromagnetic spectrum again, but we're going to talk this time about the light that it gives off and how we know what color that light is going to be. And there's a way to know that, and so we're going to use this today to figure this out. The first thing we need to know is the definition of what a photon is. A photon is a particle of electromagnetic radiation, and the photon is what it gives off. And we're going to go into a lot more detail with that. The different wavelengths of electromagnetic radiation carry different amounts of energy. For example, the photons that correspond to the red light, so we see the red down here, the red light carry less energy than the photons that correspond to the blue light in the purple lights. In general, the longer the wavelength, and we need to have this, the longer the wavelength, of light, the lower the energy. And so we can see that here in this picture. As we look here, the wavelengths of the red are much longer than the wavelengths of the purple. And that's what they're talking about. So the ones with the more energy are the shorter wavelengths. Okay, so what's happening here, these are some different spectrums that you'll see when we look in the tubes today. And the tubes that we're going to be looking in are called spectroscopes. And that's where we see these different colors and these different things given off, and the spectrums given off. And what you're seeing here in this picture are different spectrums for different specific lights. And you can see here, this one's hydrogen, this one's helium, this one's mercury. Actually, I believe those are above. I'm sorry, this one up here above is the sun. This one is hydrogen, this one is helium, mercury, and uranium, and so the different lights that they will give off. Atoms receive energy from some source and become excited. This is how this whole thing works, and I'm going to draw a diagram on the next page, but what we need to know is that they have to receive energy from some source, and they have to become excited. What happens then is they release the energy by giving off the light, and what we're seeing here is the energy that is carried. The emitted energy then is carried away by the photons. Energies of photons correspond exactly to the energy change experienced by the emitting atom. High energy photons have short wavelength light. Low energy photons have long wavelength. Photons of red light carry less energy than that of the blue. We already know that. Tomorrow we're going to do a flame test lab, and you can see these different colors of flames here in this picture. And what happens is the colors of the flames result from the atoms in the solution releasing energy by emitting visible light of the spectrum. And so this is just different chemicals that we're going to be using to make these different colored lights, and it's all a color of the spectrum because that's how much energy it's given off. So this is the most important slide right here. We need to talk about what is happening is we have our element or our atom, and that atom is in its what we call ground state. And so in its ground state, it's not going to give off this photon of energy. What happens is as we have the atom and we add energy to the atom, then the atom becomes excited. And we need to know those terms. So it goes from its ground state to its excited state, and it only will do that with the addition of energy. So what happens then, once it gets to its excited state, we now have this little atom up here, and as it comes down back to the ground state, unless you continue to add energy, it will come back down to its ground state. So what happens is the wavelength that it comes back down on is then going to emit that photon, that particle, and whatever that wavelength is depends on the color. And so if it is a really long wavelength, it would tend to be low energy, and that would be more of a red color. If it is a short wavelength, then as it gets shorter, it's going to go up the spectrum and closer to the darker purples. Okay, light corresponds to different energy levels. When we have high energy light, we have short wavelength. We've already talked about this on the previous page, but just a reminder. And so when we have low energy, we have longer wavelengths, and they correspond. Oops, that should say long. And that's where we get these different colors that we see in this spectrum over here. Barium would have low energy or high energy. I want you to tell me for each of these what kind of wavelength and what kind of energy they would have based on their color. Just a reminder of the terms here on this page. The excited state is the highest possible energy state, and so we have to get the atom to that state. The ground state is the lowest possible energy state. This is a hydrogen emission spectrum tube, so as you look through the spectroscope, these should be the colors you see with hydrogen. Now, the difference here is these are probably very good spectroscopes. Our spectroscopes probably aren't quite this good, so you're going to have a hard time pulling those colors when you look at our hydrogen tube. Because only certain photons are emitted, we know that only certain energy changes are occurring. Excited hydrogen atoms always emit the same photons with the same discrete levels. So what that's saying is you can expect a pinkish line at 410 nanometers, at 434 nanometers, a blue line, a green line at 486, and a red line at 656. We then can conclude that all hydrogen atoms have the same set of discrete energy levels. And so that's what they're talking about here, is this is the discrete energy level. And then when we look at a hydrogen atom, it should give off, if we have a good spectroscope, it should give off that exact same emission. So when we look at the light, we know exactly what chemical is causing that, or what atom. Okay, so this diagram looks a little bit scary, might you say, but there's a couple terms we need to know about. Quantized. Only certain values are allowed. That's what the word quantized means. And what they have found, scientists have found that the energy levels of all atoms are quantized, which means we can look at the light and see that energy level. And so what's happening here, in just a description, what they believe is happening is as those energy levels jump, as we excite an atom, the atom jumps, or the electron jumps to another energy level. And as that's coming out, that is the light given off for it to jump and come back to its energy level. A little analogy to use is ramp elevations, which are continuously varying to that step, which elevations are discrete. And so what they're talking about there, think about this as a ramp, okay, versus a set of steps. This is a discrete step. These are continuously varying, and that's what we're looking at. There are steps, and then there are the ramp. So what they're saying then is that the electrons behave as the steps. There is a discrete energy level and there's a specific jump that those atoms are going to make when they're excited. So then comes exactly where we've been going all along through here, is the wave mechanical model. In the 1920s, de Broglie set out to understand the electron's position, and we've talked about this. This is our bug zapper analogy that we've used here. And this is kind of a picture of what they believe it to look like, and understand the electron's position in a different manner. He believed that light had both wave and particle characteristics. The electrons may also exhibit both of these properties. So again, what he thought was happening is as that electron came out and then came back in, as it is jumping levels, which we know it does, it emits a light. And that light then, and it behaves like a wave, so it gives off its photon of light, and then as it comes back, and so we're most likely to find those, as you notice, closer to the nucleus, we see more green, and as it comes off here, we see those more and more color, and that's what his theory is.